All right, what's up? Today we're going to talk about identification and models. So we've still been developing some unambiguous language to use to describe random phenomena in the real world. And this week we're going to figure out how we can use that language to actually talk about whether or not we can estimate causal estimands of interest. So in our graphical abstract here, we did probability theory. We did statistics, where the basic idea is we've used probability theory to define some quantity that we're trying to estimate. And then we use that, and that's defined in relation to some unknown data generating process. Then we assume our data is drawn from that data generating process, and we would like to use that data to guess what that unknown number is. And that's what estimators do. And then we talked about inference, which is then how do we quantify the uncertainty? Understanding that the data that we got are just one possible data set that we could have drawn from that data generating process. And so we could have gotten a different answer if we had did it again. And we'd like to quantify the uncertainty in that process. And then we went back a little bit to probability theory. And we say, okay, well, we talked about data generating processes and estimands, but what we really want to ask about, the kinds of questions that we're actually usually interested in, are causal. So they have to do with what would happen if I did this versus what would happen if I did that. So is it better, for example, to treat diabetic people with metformin as a first stage treatment, or is it better to put them directly onto insulin? How do you compare? How do you say which of those is actually more effective in terms of reducing blood sugar levels long term? And so to be able to formally ask what is that question actually talking about, how do we put that into the language of probability, we introduce potential outcomes. And today we're going to talk about identification, which is kind of tying this into the statistics world, because we saw that for potential outcomes, we don't really get to observe the things that we actually kind of would like ideally in order to be able to estimate what we want to estimate. So we don't get to see for a given person both what would happen if I did one thing versus what would happen if I did another thing. And so if you're kind of missing some important information there. So that was what we described as the fundamental problem of causal inference, which is that if you're comparing this drug versus no drug, you either get to see the person take the drug or you get to see the person not take the drug, but you never get to see both. But what you really want is to compare those two potential outcomes to each other. And so you end up with data that looks like this, where you have this A is the symbol that I use to refer to a random variable saying whether or not you got this treatment of interest. So this could be drug versus no drug. This could be exposure to a chemical pollutant versus not. This could be somebody who got a surgery versus a different kind of surgery. It could be living in a particular area or not. So this is the exposure or treatment that we're interested in. And then we have the outcome that we observe. But this outcome is really just one of these two potential outcomes. So for this person who didn't get treated, we get to see what would have happened if they didn't. But we also have to imagine what would have happened to this person if they had been treated. And that is something we don't get to see. Relative to with this person who was treated, we get to see what happened when they were treated, but we don't get to see what happened had they not been treated. So these are the unobserved potential outcomes. And we just get to see the observed potential outcomes, which are the ones that correspond to the treatment assignment of that person. Now, our question is, if we've defined, for example, this causal estimand, the ATE, which is the average had I treated everyone minus the average had I not treated everyone, well, those quantities depend on these missing data, right? And we don't have that. So how the hell are we going to estimate this thing if we're missing that data? So is it even possible, right? Like let's make it as easy as possible. Let's say we had infinite observations, or like we have the entire population. We observe the entire population, so there's no kind of like sampling problems. We don't have to think about uncertainty or anything. We just are trying to estimate this, we have to calculate this thing. But even with infinite data, we're still missing these potential outcomes. So is it even possible to do this? And the answer is, which we're going to talk about, sometimes actually no. Sometimes it is not possible. So here's an example. Let's presume that in this data generating process, nobody gets the treatment. So everyone is getting standard of care, or everyone is getting placebo. And so let's say this is a new drug that's never been used before in the population. You just have no data about it. So nobody has gotten it. So you're missing all of this. So of course it's impossible to estimate this part. Now, yeah, you can estimate this part, but this is impossible to estimate because you have literally no data about it. So it depends, right? Because here's an example of a data generating process where A is always 0, and it's impossible to do what we're trying to do. But here's an example where it is possible, and I'll show you why. So presume that the treatment is randomized, that whether or not somebody gets this exposure, I decide it based on flipping a coin. So half the people we get to see this potential outcome, the other half we get to see the potential outcome. But who gets to be in which bucket, so to speak, is decided purely at random. And I claim that in this setting, we can actually get at what this number is, and I'll show you how. So that it relies on everything that we've learned about independence and expectations. So if A is randomized, then the exposure is actually independent from everything, right? Because the source of randomness that goes into it has nothing to do with any of the other variables. So actually A is independent from everything else. And since it's independent from everything else, in particular, it's also independent from this potential outcome, what would have happened under treatment. And since it's independent by the definition of independence, the probability distribution of y1, this potential outcome under treatment, is equal to the conditional distribution given A equals 1, because A doesn't tell us anything about the distribution of y1. And since it doesn't tell us anything about the distribution, in particular, it also tells us nothing about the expectation. So this is a property of expectation and independence. And now this is all I'm doing here is saying that the observed outcome for people who were treated is actually just the potential outcome under treatment. So if you look at this data set here, now if I subset it to just the people who have 1s here, and I ask about what is y, well, it's y1. So in this subset of A equals 1, y1 and y are the same thing. And so that's why I can substitute. Here I'm looking at just in this subset, A equals 1. And in that subset, I can substitute y1 for y or vice versa. So I've gone from the expected value of y1, which is part of what I want, like it's this thing here, and I've shown that this is actually the same as this conditional expectation, which has no potential outcomes in it. Now I'm just talking about the observed outcomes, right? So there's no reference to potential outcomes. This is something I can actually estimate from real data. This is in fact, and if I repeat this whole thing with y0, I can show that this equivalent quantity here is equal to the same thing, but with A equals 0 here. And so if I take the difference of this minus the A equals 0 part, that's just the naive ATE, which is what we were saying last time sucks. It's bad, right? We can't use it because it's not actually paying attention to these potential outcomes. But what I've shown is that in this special case, where if A is randomized, we can actually use it, in the sense that it's the same thing. And that means that if we have a finite data set, right, we can just use this naive ATE estimator. As we have more and more data, we'll get closer and closer to the right answer because this thing is asymptotically normal, centered at the true mean. And so with more and more data, we'll get closer and closer to the true answer, which is great. So we can use the data in this case. And we'll get more into that in a minute, but let's just ask why. What's going on here? Remember last time we talked about confounding and how that's a problem, and that's why the naive ATE estimator doesn't work, because it's kind of estimating the wrong thing. But in this case, randomization actually eliminates the confounding. So we had this single world intervention graph or directed acyclic graph, and before we had an arrow going from X to A, where X is some confounding variable like somebody's age, which could impact whether or not they take the drug or not, which then impacts their later blood pressure or something like that. So here, that arrow from age to the treatment has been broken because I randomized the treatment. So now treatment has nothing to do with age, and therefore we do not have confounding. So there is no variable that impacts both treatment and the outcome. So visually, I think it helps to look at the kind of data points here. So let's imagine we could observe everything we want to. We can see both potential outcomes, playing God here. So here we have the different data points. So here X is like the confounder, like somebody's age, and then each kind of pair represents one person. So this is what would have happened to this person if they were treated versus what would have happened if they weren't. So here, like, treatment lowers everybody's blood pressure, if you want to use that concrete example. And we saw, okay, what the ATE is just the kind of average, the kind of y-axis average of the red or the pink stuff. The difference between that and the y-axis average of the gray dots. Cool. That's the truth. That's the true causal ATE, where we can observe both potential outcomes for everyone and average those columns and take the difference. Now, what happens when we have confounding is that, let's say, if people who are older are more likely to be taking this drug and younger don't take it, right? So if we take the difference in the sample averages when there's confounding, there's a problem, right? That naive ATE in this example is going to be a big underestimate of the truth, and we're really not getting at the right thing. But randomization actually fixes this because it rules out this case. I'll show you what I mean. When you randomize the treatment, the pink points, the distribution of the pink points on the x-axis is statistically the same as the distribution of the gray points. So you're never going to end up with this case, or it's very rare, it's very improbable to end up with a case where, like, you have all the pink people over here on the high, all the older people getting treated and all the younger people not getting treated. By randomizing, you've kind of spread these both out along the x-axis, and indeed among any other possible axis you could imagine. Age, whatever, it's independent of everything because you randomized. So you've made sure that the two populations, the treated and the untreated populations, are the same, have the same distribution of everything. And so the only difference that you're observing is the difference in the effect of treatment. So that fixes the problem. And when you calculate just the naive ATE here by taking the average of these four and the average of those four, basically these 4 points stand in perfectly for that whole distribution, and these four are representative of this whole distribution. And so the naive ATE you get in this case is actually the same as the causal ATE. So here in writing, I've basically said that distribution of age or anything else among these two exposure groups is the same, which means that the difference in the outcomes between the two can only be due to the exposure differences, right? And so that leads to this question, which is, when approving new drugs, why does the FDA only consider evidence from randomized trials to be convincing rather than evidence from an observational study? And at this point, this should be kind of clear, right? Like, if you have an observational study, you could have this, right? So whatever number you're reporting, it could be pretty bad. It could be pretty biased. Whereas if you're in a randomized trial, you're guaranteed to have no bias, right? You could have some variance. There could be a little bit of a variability, which will, once you get to the estimation part, but at least the thing that you're estimating is actually the true causal ATE. Let's do this little problem here. So imagine this is the entire counterfactual population. And the questions are, firstly, is A independent of Y1 and Y0? Secondly, we add the column indicating the observed outcome, and then we calculate this conditional expectation of Y, and we calculate the marginal expectation of Y1. So have a shot at that yourself. Okay, so let's do this. Let's work through this. So first one, is A independent of Y1 and Y0? So if you recall, the definition of independence, let's just do it for Y1. This just means that the distribution of Y1 is the same as the distribution of Y1 in any subpopulation of A, defined by A. So we can just check this. So the marginal distribution of Y1, so here Y1 is a binary variable, and so Y1, since this is the entire population, all we need to know about it, it has to be Bernoulli. That's the only distribution it can be if it's binary. The only question is, what's the probability? That takes the value 1. So it's 1, 2, 3, 4, 5, 6 out of 8. So 3/4, right? And the question is does it have the same distribution when we condition on A? So if we look at just A equals 1, for example, is this 3/4? Yes. If we look at just A equals 0, is this 3/4 Bernoulli? Yes, it is. So that was Y0. But for y1, it's the same. So y1, it's 1, 2 out of 8. And then in these subpopulations, it's so that's 1/4. And the subpopulation is 1 out of 4 and then 1 out of 4 as well. So indeed, A is independent of both y1 and y0. So next step, let's add a column indicating the observed outcome here. So I'll just write that here. For this first person, the treatment they got was 0. And so what we see here is the y0 outcome, which is 1. Although the y1 outcome is the same thing, but with this one is coming from here. Next person, their treatment is 0, so we got this 0. For this person, their treatment is 0, so we get y0. For this person, their treatment is 0, so we look at y0. So we're getting these numbers. But for these people, we're getting these numbers here. So it's 1, 0, 0, 0, right? This person was treated, and so their observed outcome is the potential outcome according to treatment. It's that one. So these are our values for the observed outcome. And now let's calculate the expected value of y given a equals 1. So in the subpopulation that's treated, what is the mean value of y? It's 1 out of 4, right? And then what's the expected value of y1 of this entire column? That will be 2 out of 8, which is equal to 1 out of 4. So what you should notice here is that we have this assumption, or this data generating process satisfies this condition. Okay, this population satisfies this condition that A is independent of y1 and y0. And as a result of that, we actually have this equivalence between this mean of the observed outcome in a subgroup and the marginal mean of this potential outcome, which is really what we care about for causal effects. So hopefully this has helped kind of show in a very concrete worked example in a small population how these things work. So let's look at another case. So let's look at this case here. So all I've done, I've switched who gets what treatment. Okay, so this is what we were looking at before, and now we have this. So now these two people are getting the treatment, and these two people are not getting the treatment. So let's do the same thing. Asking about independence. So let's look at the distribution of. Let's just look at y0. The distribution of y0, is it the same in the control group and in the treated group? So in the control group we have 2 1s, and in the treated group we have 1, 2, 3, 4 1s. So they're different. So by conditioning on a equals 0 versus a equals 1, we get different distributions of y0. Therefore, those things are not independent. A and y0 are not independent. And same for y1. For y1 we can consider, maybe let's look at the marginal distribution versus the condition. So in the marginal we have the probability that y1 is 1 out of 4, or 2 out of 8. But in this subgroup of treated people, the distribution is, we just have 0, all zeros, right? So the distribution is the probability of getting y1 is 0, which is not the same as 1 out of 4. So those a and y1 are not independent. Okay, so let's mark that as a no here. Let's add this column indicating the observed outcome. So for these people, it's going to be these two numbers. So we're going to get y, 1 and 0. These guys is going to be these two, 0, 0. For these two, it's these two. And here, 0, 0. Okay, so this is the observed outcome for each person. Let's calculate the mean of y in the subgroup where a equals 1. So a equals 1, and we're taking the mean of y. So that's this number, this number, this number, this number. It's 0. Okay. And what about the mean of the potential outcome? That's the same as what we had. Sorry, this one calculated before. It's 1/4, because that number didn't change. I just changed who got treated, right? So here, these two things, they are not the same. Okay. And this is actually due to this. So if we had these observed data, even though causally it seems like, yeah, the treatment does have some effect, you can see that here, right? So for this person, the treatment didn't change anything. Okay, they were going to have the outcome no matter what. That's what this says. For this person, the treatment didn't change anything because they were not going to have the outcome no matter what. Okay, so let's say this outcome is like a heart attack or something. For this person, the treatment helped because, or would have helped, I should say, because if they don't have it, they have a heart attack. But if they do have it, they don't. So we're helping this person. For this person, we're helping. For this person, doesn't change anything, and then these two people, it helps prevent the heart attack. So in half the people, this drug is preventing a heart attack, and the other half, it's not doing anything. So it's definitely helping here. But if let's compute the other conditional mean equals 1. Sorry, a equals 0. That's okay. Y given a equals 0. That's these groups. So we have a 1, a 0, a 1, and a 0. That's 1/2. Okay. And then let's compute 1 and 0 is 1, 2, 3, 4, 5, 6. 6 over 8. Okay, so the difference of y1 and y1 minus y0 is 1/4 minus 3/4. This is the true causal effect. Is minus 1/2. Right? The difference the difference between these the kind of naive causal effect is actually also minus 1/2, but it's almost an accident, right? Because you see these two numbers are not the same, and these two numbers are not the same, but yet the difference of the two is actually still minus 1/2. Sorry, that can happen sometimes. So that's a kind of funny example here. But my point should have been that there are cases where the treatment actually is doing something, but because of the way that it was assigned, it makes it look like it's not doing something. So we maybe a better example would have been, let's say, like all the people for whom it would have worked. Let's see what we're doing here. Yeah, I see what's happening. So the people who are getting the treatment are the people for whom it's preventing it. So what you should do, try this for yourself. See what happens. I mean, I'm not 100% sure if this will work, but try for yourself. Change these numbers. Okay, so change these to zeros, and then let's say change these to ones. Let's see what happens there. So there we have all. So just follow the same process that we did, and you can see what the kind of naive treatment effect is based on the observed outcome, and do that, and then maybe also play around with it, right? See how big or small you can make it by just changing the treatment assignment, who gets the treatment and who doesn't, and hopefully what you get out of that is seeing that the causal effect can be very much obscured if the treatment is assigned in a way that it looks like the people who are getting the drug are those who are benefiting, or those who are not, or those who are not benefiting, and things like that.